Hello, this is part 2 to my last major video titled The Power Grid, Isolation Transformers and Earthing. You can watch this video as a standalone episode, but I still recommend you to watch part 1 if you haven't done so yet. In that video I also told you that I'm working on 2 isolation transformer units. In this video I will talk about the unit on the left, because it is better suited to explain the principles involved without going too much in the details. I will also try to answer those questions formulated in part 1, which are still unanswered, as well as to further explain the possible applications I mentioned. Along the way we'll talk about isolation transformers, Variacs and Autotransformers. But since we had so much theory in part 1, let's start with only the simplest ideas and get to some real-life action as fast as possible. What I call an isolation transformer unit is a device which combines at least 2 capabilities. First, delivering a non-Earth referenced AC supply voltage at the grid level, in Germany that's 230 volts, and second, allowing continuous adjustment of the output voltage while leaving waveform and frequency as unchanged as possible. To accomplish that, you would need either an isolation transformer with a movable tab at the secondary side, or a 1:1 ratio isolation transformer plus a Variac, which is actually just a trade name for variable autotransformer. While commercial products might employ the first solution, the second one is the more common approach if we are talking about DIY projects. The unit I'm working on employs additional electronics, for example a turn-on current limiting circuit and some safety features, but more about that later in the video. So let's have a look at how I actually built my unit. Other than most projects, this one started with an aspect that is regarded as non-essential by many hobbyists these days: finding the right enclosure. My idea of the look that heavy equipment like this should have is this Rode und Schwarz frequency counter built in 1962. I regard this early Cold War type of enclosure as the epitome of style and ruggedness. That's why I decided to tear down this 1953 Rode und Schwarz AM transmitter, which is lying around in my labs for 3 years now. There is no way I was ever going to restore it, and that's why I scavenged it for parts, sold them on eBay and kept the enclosures as a base for this and other heavy projects. The transmitter is comprised of 6 heavy rack mount modules. Tearing them down was a lot of work, and I will only show you a small fraction of that. This module is the high voltage power supply of the transmitter. It is based on this high voltage transformer weighing 24 kilograms. Getting it out of the enclosure involved some unscrewing and cutting of wires. This is a large selenium rectifier which was used to rectify the 2.3 kilovolt AC coming from the transformer secondary. To smooth out the ripple voltage, this Bosch brand high voltage capacitor was used, followed by some voltage divisors built from wire-wound resistors, manufactured by the German company Rosenthal. The transmitter, by the way, was built for the US military. That's why the signs on the front panel are in English. The manufacturing date is from 1953, as this stamp reveals. The enclosure is very dirty though. It must have been exposed to heavy exhaust fumes for some time. But yet again, the old soapy water method, which you might know from my repair videos, worked quite well. Here, a comparison picture. With the enclosure cleaned and dried, it was time to install the most important components: a 1 kilovolt ampere isolation transformer and this 10 ampere Variac. This isolation transformer looks a bit old-fashioned, but it is actually a fairly modern model, built in 1997 by SBA in Germany. For those of you who are interested in it, here is the nameplate. This kind of transformer core is called a UI core. That's because it is comprised of metal sheets formed like U's and I's. You don't see this core type very often. In fact, most 50 Hz transformers these days have EI cores. The transformer has 2 parallel primary and 2 parallel secondary windings, which are wound to 1/2 on the first and to 1/2 on the second limb of the core. Installing the transformer on the steel frame of the old enclosure was no problem. I also installed this small 12-volt auxiliary transformer, which I need to supply the additional circuits that I will explain later in the video. The Variac needs to be mounted on the front panel itself, which is basically a 4mm aluminium sheet. A couple of holes for the axle and the 3 screws need to be drilled. In addition, 2 large holes for the 2 sockets are needed. For that I used the Black & Decker jigsaw, which you might still know from my Repair and Tear Down Sunday video. With some additional holes for the on switch and a signal lamp, the front panel is ready for the Variac to be installed. The Variac itself is held in place by 3 Allen screws. With some more work done, the most important components are now in place. The Variac with a big black knob, 2 sockets, an on switch and a signal lamp. In addition, I have now installed these steel bars on which I will place the circuit boards, which will add additional capabilities to this device. After installing a 3rd steel bar, I also added another 200 VA transformer. It will deliver 12 volts at a maximum current of 16 amperes for a secondary side switched mode power supply. An additional feature that has nothing to do with the basic isolation transformer though. I have also built a simple turn-on current limiting circuit based on the 555 timer. I then also added some safety features. I connected the metal parts of the enclosure with a protective earth, as it is common practice with stationary units. The sockets on the front panel, however, are not to be connected to the PE. In fact, I even removed the earth connectors from the sockets entirely. I then added several fuses and a temperature switch which sits on the core of the 1 kV ampere isolation transformer. The unit is now ready for basic operation, and I will now show you some applications as I promised at the beginning of the video. After that I will give you some explanations of the components involved and the theory behind their operation. So let me show you some examples for possible applications. My first point from part 1 was that you could use an isolation transformer unit for experimenting on offline switched mode power supplies. To understand what I'm talking about, you must know some basic facts about SMPS. A typical offline SMPS works on the following principle. The 230 volt from the power grid are rectified. The pulsating DC voltage from the rectifier is then used to charge a large electrolytic capacitor, sometimes referred to as the bulk capacitor. In real life, it would look like this one. The voltage across the charged bulk capacitor will be around the grid voltage times the square root of 2. In Germany, that's roughly 325 volts DC. Now, here lies one major reason why it is dangerous to experiment on switched mode power supplies without an isolation transformer between its input and your electric outlet. The voltages inside the primary side of the switched mode power supply, and especially the voltage across the bulk capacitor, are directly connected to phase and are thus earth referenced. Meaning that if you would happen to accidentally touch the wrong points on the PCB, you would either be exposed to 230 volts AC or even 325 volts DC. An RCD or GFCI might give you some protection in the first case, but might not be able to stop the bulk capacitor from discharging into your body. In the case of many high-quality, high-power SMPS, you will also have a boost converter between the rectifier and bulk cap, which will even again step up the DC voltage to a value around 400 volts. The boost converter is part of what is called active power factor correction, APFC. Such a power supply, of course, involves many more systems, like the main converter circuit, here a so-called double-ended forward converter. Furthermore, you would have an auxiliary power supply, the main control circuit, an inrush current limiting circuit, and many other systems. But I just said that to mention it. I will not go into the details here because this is not the topic of the video. Furthermore, when working on the primary side of such a power supply with your oscilloscope, but without an isolation transformer, you might get into trouble because your oscilloscope might be earth referenced. But there already is a great EEV blog video about this problem. It's titled How Not to Blow Up Your Oscilloscope. And I will copy the link in the video description. I highly recommend it. An isolation transformer unit can also be used to test the behavior of an SMPS under certain fault conditions. What you see here is a 725 watt HP server power supply. 2 of the control pins are bridged, so that it will automatically start up as soon as a supply voltage is detected. I connected a 12 volts 20 watt halogen lamp to the output of the power supply. The left DMM measures the DC voltage across the bulk capacitor, while the right DMM measures the value of the 50 Hz AC supply voltage delivered by the isolation transformer unit. According to its nameplate, the PSU should at least operate with supply voltages between 100 and 240 volts AC. I will now start at a supply voltage of 230 volts and slowly step it down until the PSU fails. So, at least with a 20 watt load, the PSU manages to work until the supply voltage drops under a value of around 40 volts. It is apparent that the boost converter inside the APFC circuit also maintains the voltage across the bulk capacitor over 390 volts. When we reached 40 volts supply voltage though, it seemingly stopped to work. Now let's step the voltage up and let's look when the PSU will start up again. So, as the voltage rises over a value of around 80 volts, the power supply kicks in again. There's basically no way to know the performance of such a unit during an undervoltage condition like this if you wouldn't have an isolation transformer like the one I use. A feature like this is especially practical if you live in a country with a 230 volt grid and you want to design a power supply for a 110 or 115 volt system. This is a good way to simulate that condition. And speaking about 115 volts, we are already at the next application which I mentioned in part 1. What I hold in my hand here is a tangential fan, as you can find it for example in projectors and storage heaters. It's powered by a shaded pole induction motor. According to a sticker on the back, it's rated for 110 volts and not for the 230 volts typical for my country. To power it up and to see if it delivers enough air, we can connect it to the isolation transformer. By slowly stepping up the voltage, I can determine its minimum operating voltage. Here it's somewhere between 50 and 60 volts. I can also find out how it will perform at somewhat higher levels than it is rated for. You now might ask yourself if it isn't possible to do the same thing with a phase-fired controller like the one I used in my air compressor video. To answer that question, let me demonstrate. As you can see, the motor won't run. When I further increase the firing angle, the motor moves, but only very poorly. Why? Well, an induction motor like this requires to be supplied with a current having a waveform that comes at least near to a sinusoid. It doesn't like the chopped off shape that the phase-fired controller delivers. One of the advantages of a Variac is that it doesn't change the waveform of the supply voltage in a major way, like a phase-fired controller does. But enough of that. Let's come to the next point I made in part 1. I said that you could use an isolation transformer like this to work on old equipment, like for example tube radios. What I meant was that it can be something of a gamble to turn on an ancient piece of electronics with probably dried out capacitors and other components that are barely working. Sometimes it might be a good idea to supply a device like that with a low supply voltage and find out if it is principally still somewhat operational without putting too much stress on its parts. Let me show you what I mean. This is a vacuum tube based radio from the year 1955. It's a Löwe Opta Rheingraf to be more precise. I bought it from some guy in the neighboring village for €1 without knowing if it still works. I connect it to the isolation transformer and I will supply it with a voltage of let's say 180 volts or something.
Es ist ein Hören. Liebenswerte zugleich. Wie er dasteht. Die Worte den sich überlagernden Gedanken hinterherstürzen lässt, mit temperamentvoller Zunge, herrischer Gestik der Hände.
So, as you can see for yourself, it kinda works and hasn't gone up in flames yet. This of course is just a fringe application of an isolation transformer, but there are other uses that I mentioned. But what I meant with the other 2 points will become evident as we proceed through this video. Now that you have seen some practical stuff, I guess it's about time I tell you how different kinds of transformers are built, how they work, and how I connected them together to build my isolation transformer unit. So, in this final part of the video, I will try to answer the following questions. First, what exactly is the component called isolation transformer? Second, why do you need to limit the turn-on current? Third, how did I implement current limiting in my unit? And fourth, what is an autotransformer and especially a Variac? So I will now start to answer these questions. I will keep it simple and short. If you need additional background information, I recommend you to watch my SMPS tutorial part 5, where I explained some inductor basics. All those basics can be directly applied to transformers as well. So let's come to question 1. Per definition, an isolation transformer is every transformer that is equipped with at least one primary and one secondary winding. The 2 windings must not be connected with one another, and the secondary must be able to deliver a voltage that is isolated from the primary voltage. That means that no defined voltage exists between any point on the secondary with respect to any point on the primary winding. In theory, this is true for most transformers you will ever see. But in practical electrical engineering, such a transformer is only called an isolation transformer when the secondary voltage is roughly equal to the primary voltage. Otherwise, this component is just called transformer and not isolation transformer, even though both rely on the very same principle. Earlier in the video I also mentioned that there are commercial units in use which utilize an isolation transformer with a movable tap on the secondary. I don't have such a part, but what I have is this old variable transformer for model railroads. When you open it, you can see that it has a movable copper wiper contact which wipes over the exposed turns of the secondary winding of a transformer. This device delivers electrical isolation and an adjustable AC output voltage, but does only deliver a maximum voltage of 16 volts. So let's come to question 2. Why do you need to limit the turn-on current? For that, let me just show you a little experiment. This is the 1 kilovolt ampere isolation transformer which I use for my units. I will now connect it directly to one of my electric outlets. What did just happen? Why did the lights go dark? Well, my circuit breaker just blew. And there is a good chance that this will happen to you if you connect any high-power transformer directly to your outlet. Even if, like in this case, no load at all is connected to the secondary. But why does this happen? Well, let's return to this graphic. The current through the primary winding is limited by 3 factors. The inductive behavior of the primary winding itself, which should resist the build-up of a current through it, the resistance of the winding, and the internal resistance of the voltage source. But since we are talking about the mighty power grid here, the internal resistance is negligible. In a large transformer like this, magnet wire with high cross-section area and thus high conductance is used. The wire resistance is thus also very small. That means that we have to trust in the inductive behavior of the primary winding to operate a transformer which is connected to the grid via a circuit breaker. But why does the transformer not show this inductive behavior in the moment where it is first turned on? Well, the reason is an effect called remanence, and it has to do with the iron core of the transformer. Because I don't want to go too deep into physics in this video, I will use a model you might still know from high school. The model of the elementary magnet. Imagine that inside the core there are small pieces of iron which act as elementary magnets. When, in the positive half wave of the sinusoidal AC, current is flowing through the winding in this direction, according to the right-hand rule, the magnetic flux inside the core will have this direction, and the elementary magnets will align with it. When now the negative half wave of the AC period begins, the elementary magnets will turn around. This will go on and on as long as a sufficiently strong AC is flowing through at least one of the windings. When the current is turned off, the elementary magnets will reorient themselves in a chaotic fashion. But chances are that a certain portion of the magnet stays aligned with the magnetic flux from the last half period when current was still flowing. Thus, a remanent magnetic flux will keep on flowing through the core even though no electric current is flowing anymore. In other words, the core behaves like a permanent magnet and the remaining magnetic field is called remanence. The iron core will stay in this state as long as no external magnetic field changes the situation. When the transformer is now connected to the grid again, as I did in the footage I just showed you, and it happens so that the first half period of the current has the same direction as the last one when the transformer was turned off, the primary winding will try to magnetize the core in the same direction. But because a large portion of the elementary magnets already points in that direction, the inductance of the winding in this moment is very small, and it will barely resist the build-up of the current through it. Therefore, a large current surge occurs and the circuit breaker blows. The state in which all elementary magnets are already aligned, but the winding might still try to further build up the magnetic flux, is called magnetic saturation. In most cases in power electronics, magnetic saturation is a very bad thing, and we try to avoid it. To avoid the current surge, a resistor is connected in series to the primary winding, just like the one you see here. In parallel to the resistor, a relay is then placed, which is supposed to close shortly after the current surge has been limited to acceptable levels. And this already brings us to question 3. How did I implement current limiting in my unit? For that, I will show you the core circuitry of my unit so far. Not included is a programmable switching converter that is still in an early experimental phase. This is basically just an isolation transformer with a Variac on the secondary side. A mains switch is activated. At this moment, the isolation transformer is being connected to the grid only via 2 series resistors. At the same time though, a small auxiliary transformer is directly connected to 230 volts. It doesn't require current limiting because its primary winding is made of low cross-section area magnet wire and has thus a very high wire resistance that prohibits a large inrush current surge. The secondary voltage of the auxiliary transformer is then rectified and regulated by a small linear regulator. It then powers and resets a timer circuit based on the NE555 timer. The timer then activates the relays, which short out the resistors in series to the isolation transformer's primary winding. The delay time is a fraction of a second. I used 2 relays for experimental purposes. 1 relay and 1 larger resistor would have done the job. The 200 VA transformer for the secondary side switch mode power supply I'm still working on is connected in parallel to the isolation transformer's primary. The auxiliary transformer will also supply some control circuits that I will later need for additional features. So now that we have been talking about that too, all that remains is to talk about Variacs and to see how you could get DC voltages from this thing. So, what is an autotransformer and what is a Variac? Well, let's again return to this graphic of an isolation transformer. We now remove the secondary winding and apply an AC supply voltage to it. It now happens that across each single turn a voltage drop, which I call V-turn, occurs. This voltage is the supply voltage divided by the number of turns. If you now tap one of the turns, you can use it to get a supply voltage which is basically the sum of all turn voltages up to this point. In other words, you can step down the supply voltage without even the need for a secondary winding. That's what you call an autotransformer. And we can just build our own autotransformer to prove this theory. This is a toroidal transformer with a primary winding for 230 volts and 2 secondary windings for 12 volts. The secondaries are easily recognizable because they are wound of wire with much bigger diameter. I will now remove the secondaries. And also the insulating tape that covers the primary. Now I scratch off the insulating layer on some single turns of the primary and solder some wire to it. This is now an autotransformer with 3 taps. To test it, I connect it to my isolation transformer unit. Instead of supplying it with 230 volts, I supply it with just around 30 volts. In this way, you can use the unit to test all kinds of transformers relatively safely. And as you can see, the voltages at the 3 taps are all smaller than the supply voltage itself. But it is also possible to use an autotransformer to step a voltage up. For that, you simply use one of the taps to supply the transformer. Here I supply one of the taps with around 30 volts to step up the voltage to 230 volts and to power this light bulb. And now a Variac, which as I said before is just a trade name for an adjustable autotransformer, is not much different from the self-made toroidal autotransformer you just saw. Only this time, not just single turns, but all turns are exposed at the backside of the toroid. There, a movable graphite electrode slides over the exposed copper turns, tapping the primary. Graphite is used instead of a copper contact because, due to its relatively high resistance, it can touch several turns at once without damaging them by creating a direct short as copper would. It also allows finer adjustment of the output voltage because it acts as a kind of voltage divider between 2 neighboring turns. What we have here is an old 120 volt Variac that was made by Stako in Dayton, Ohio. Anyone out there from Dayton, or at least Ohio? I send my best regards to you. Please leave a comment if you're from those parts. Do you know anything about the Stako company? Please tell us. This Variac is rated for a maximum current of 3 amperes at 140 volts output voltage. And that's how you should read the ratings of a Variac. The manufacturers often give you a maximum reactive power value, but that can be misleading, because the power a Variac can deliver is always limited by the maximum current. At an output voltage of 140 volts, it may be able to transform 420 VA, as it says here, but that's only true for the maximum output voltage. You simply have to multiply the output voltage times the maximum current. So for example at 10 volt output voltage it can only deliver 30 VA, and so on. This model uses a simple graphite cylinder, but other units like this German Variac use a graphite wheel to roll over the exposed turns. This model also has some additional taps. That's also the reason why it can be used to step up the input voltage. This German Variac, built by Roostrat, is rated for 4 amperes at 220 volts. This Variac has no additional taps and can only be used to step down the input voltage. With that being said, I also feel the need to warn you not to use a Variac like this to create dangerously high voltages. Do not apply 230 volts to the tap and try to create 10 kilovolts with it or something. That experiment could definitely go wrong. Now that we have talked about that as well, there is only one thing left I wanted to mention. You can also use an isolation transformer unit like this to create a DC voltage between 1 and 325 volts DC. For that you simply connect a rectifier and a 400 volt electrolytic capacitor to its output. This could be interesting for people who want to experiment with vacuum tubes, where high DC voltages like that are often required. So with that being said, I'm through with my program and we have arrived at the end of the isolation transformer series. I hope you enjoyed it and that you learned 1 or 2 things along the way.